Hello, good afternoon and to the school. I hope you enjoyed an excellent lunch and I'm really happy to introduce the next session, which is the session on similarity assessment, grouping and read across of nanomaterials. We have 4 speakers. Our first speaker is Professor Vicky Stone from Heriot-Watt University. Vicky is also the coordinator of the Gracious project, which is one of the projects co-organizing the school. We also have Agnes Omen from RIVM in the Netherlands. Agnes has been strongly involved in several initiatives related to grouping nanomaterials. Our third speaker is Nina Zelaskova from Idea Consult in Bulgaria. Nina is an expert in data management and in silico tools. Our fourth speaker will be Richard Cross from the UK Centre for Ecology and Hydrology. Richard is also involved in the Gracious project and he's an expert in environmental fate and ecotoxicology. This session will address several topics. We would start with an introduction to grouping hypotheses and the IATAs, which have been developed as part of the Gracious grouping framework. We would have an introduction to read across from a regulatory perspective, and we would focus also on the topic of similarity assessment, how similar do nano forms need to be to allow grouping and read across. Then finally, we would focus on environmental case studies for similarity grouping and read across. And this would be then the presentation of Richard, which would be our last presentation. And now I would like to leave the floor to Vicky Stone lecture. Vicky, the floor is yours.
Hello, my name is Vicky Stone. I am at Heriot-Watt University in Edinburgh in the UK, and I'm the coordinator of the Gracious project, which is funded by the European Commission. So this project has made a framework to support grouping of different nano forms together. You may be aware of the term nanomaterial. So nanomaterial is something like a titanium dioxide particle, and then a nanoform would be different versions of the nanomaterial. So it could be different sizes, different shapes, different surface coatings of that titanium dioxide. So this framework is about grouping different nanoforms together so you can infer information from one nanoform to fill data gaps for the other. And we'll look at hypotheses that support grouping and ways of collecting data via something called an IATA to support that hypothesis. So conventional risk assessment requires you to consider risks on a case-by-case basis, but this is really expensive. It takes a lot of money, it takes a lot of time, and it uses potentially a large number of animals. And so really we need to streamline this process. So grouping provides a way of intelligently streamlining your information for risk assessment purposes. Now, this is possible according to the European regulation. So the European regulation that regulates chemicals, substances and nanomaterials is REACH. And within REACH, it says that you can group together similar substances based on their physicochemical toxicology and ecotoxicology properties. So you need to be able to assess similarities. So it's fairly easy to do a qualitative similarity assessment based on expert judgment. But within the Gracious framework, we've also generated some methods for a quantitative similarity assessment, which Nina will describe to you later in this session. So the Gracious project started in 2018 and it's due to finish later this year. We have 23 partners from across Europe and 2 of those are in the US. And as I said, I've already told you, this is about making a framework to support the grouping of different nano forms. And one of those applications that you can then use the grouping framework for is to read across data from data-rich substances to those that are lacking data in order to fill their data gaps. So the Gracious framework has already been published. It was published in Nano Today in 2020, and this is a simple version of the Gracious framework. So you would start the framework either with a single nanoform that you're lacking data on to help you do a risk assessment. And so you're looking for a group that you could insert your single nanoform into that contains the data that you need. Or it could be that you have a provisional group of nanoforms, some of which have data and some don't. Then you need to go through a basic information step where you collect enough information to trigger a specific grouping hypothesis. So the European Chemicals Agency requires you to generate a hypothesis that explains why, in a scientifically valid way, the reasons that you want to group your nanomaterials together. And then within this detailed step, once you've generated your hypothesis, we then have these structures available that allow you to assess that hypothesis and gather the available information or generate new information needed. And any generation of new data would use a tiered testing strategy, where tier 1 would be simple methods, tier 3 would be more complex models, in order to generate the data that you need to assess whether your hypothesis is valid or not. If it's valid, then you can go ahead with your grouping decision. If it's not, you might either choose to refine your hypothesis and reassess it, or you may decide that you want to just assess the risk on a case-by-case basis. Applications for the grouping framework include development of dossiers for the regulator. So if you want to sell chemicals in the European Union, once they reach a certain tonnage value on the market, then you have to submit safety dossiers to the European Chemicals Agency. So it can be used to support this. It could be used in the early innovation stages of either nano forms or nano-enabled products. So if you incorporate safety into the design of such a substance, this is known as safe by design or safer by design, as indicated SBD. You also could use the framework to help you refine a testing strategy for nanomaterials, and also you could use it to help inform any precautionary measures that you want to do in terms of controlling risk for workers or for the consumer or for the environment. So this is a more complicated version of the Gracious framework. So it's the same framework as in the previous diagram, but just with more detail. So you'll still enter with a single nanoform or a provisional group that are lacking some data. And then the basic information includes physical and chemical characteristics. These can be estimated values or they could be known values, so measured. And then release and exposure information. This is important to allow you to understand routes of exposure for humans and relevant environmental compartments. Again, these could be estimated values or known measured values. And then also we want you to identify the purpose of grouping, because this allows us to understand the level of detail that you need in the outputs from the framework. This information is sufficient for you to generate a grouping hypothesis. We've already generated a number of predefined hypotheses using data from the peer-reviewed literature and from databases. I've just shown some abbreviations for a few of these hypotheses here, and we expect that this database of hypotheses will be expanded with time. If any of the hypotheses we provide are not suitable for the user, we can also generate a user-defined hypothesis using a hypothesis template. Once the user has their hypothesis, they then need to test it, and it's tested using a testing strategy known as an IATA. IATA stands for Integrated Approaches to Testing and Assessment, and I'll describe what that means in a moment. This IATA is tailored to the specific hypothesis so that you only generate the information that's really needed. When you conduct the IATA or use the IATA, it will generate information which is collated together using a data matrix, and this data matrix is required by the European Chemicals Agency for regulatory purposes. The purpose defines the level of detail and certainty within the data matrix of the information that you have, and this impacts on the number of tiers that you might include within that data matrix for any of the specific endpoints measured. Once you have your data matrix, you can then assess the similarity of your nanoform members within the group, and then either decide to accept your grouping hypothesis, to refine your hypothesis, or to assess risk on a case-by-case basis. So one of the applications that you can use grouping or the group for is to lead to read across, and Agnes will talk more about read across in her presentation later. But briefly, what this means is that within your group, so you've identified your group, there will be some nanoforms that have data available to support risk assessment, and there will be some nanoforms which lack data, and these are known as your target nanoforms. So the idea is that you use your grouping hypothesis to generate a read across hypothesis. You use your data matrix to decide whether to accept or reject your read across hypothesis, so that you then have a justified read across decision from your source material to your target material. I've also mentioned that you can use the framework in the early innovation stages. This is called the stage gate process, this diagram here. It's the gates or the stages that people might go through from the initial concept or discovery of an idea for a new nanoform or a nano-enabled product through to its launch onto the market. And so there are a number of steps or stages that the individual would go through, and between each stage are gates where you would make a decision whether to continue or to stop the discovery process or the innovation process. And we've mapped the framework onto this stage gate process. So the basic information step maps onto steps 1 from scoping through to stage 4, testing and validation, while the detailed step maps onto stages 3 from development through to stage 5, the launch of the product, when you would need to generate data suitable for a regulator. I'm now going to talk about the grouping hypotheses. So this is the hypothesis template that I described earlier on. So it helps you to generate a hypothesis that includes all of the information needed in a way that's consistent from one hypothesis to another. So it allows you to indicate the purpose of grouping, but also the context. So the context means, is it for an environmental application? Is it relevant to consumer, or is it an occupational setting? You then need to consider the life cycle stages that are most relevant to your risk assessment. So is it during production, use, or release of your nanoform into recycling or disposal? And then you need to consider these 3 questions: what they are, which covers physical and chemical characteristics; where they go, so where they go in the environment and where they go in the body; and then what they do, so their hazards. So we actually have 40 predefined hypotheses within the GRACIOUS framework, 17 for human hazard and 23 for the environment. So here are a few examples of hypotheses. The first one is for human health, and this one's relevant to quickly dissolving nanoforms that enter the body via inhalation, and it stipulates that both nanoforms and the constituent ions or molecules may contribute to the toxicity associated with that exposure, but there should be no concern for accumulation. The next hypothesis is for the environment, and it covers nanoforms with a chemical coating, and that chemical coating is not stable, so it's lost. And in the soil compartment, you would therefore need to consider both the fate and toxicity of this nanoform, and you could look at non-coated nanoforms in order to group them together. So we haven't just covered inhalation for humans, we've also looked at ingestion and dermal routes of exposure, and for the environment, we've also included the aquatic environment, sediment, and the air. This is an integrated approach to testing and assessment, or an IATA. This is a generic one. It covers exposure, phys-chem characteristics, the compartments in the environment or the tissues exposed, and the mechanism of hazard. So these are questions in a decision tree that allow you to make yes or no decisions. If you make yes decisions throughout, then you confirm your group. If you make no decision at any point, then you deviate from your hypothesis and your group's not accepted. These questions we've called decision nodes, and the questions in here are tailored to your specific hypothesis, so you have a tailored IATA. In order to make a decision, you need methods to interrogate that decision. So we provide tiered testing strategies that include a range of standard operating procedures that allow you to assess and generate the data you need to answer these questions. To answer yes or no, sometimes you need a threshold value above or below which you can say yes or no. These threshold values are really difficult to justify scientifically, and so the alternative method that we've provided are quantitative methods to assess the similarity of your nanoforms within your group. Once you've gone through the IATA and generated the information needed, then this will help you to generate a data matrix to support your hypothesis and your similarity assessment. The good thing about IATAs is it doesn't just focus on the generation of new data. It allows you to combine existing data from the literature and databases, as well as using computational approaches in order to populate your data matrix, shown here, with information so you can decide whether your nanoforms are similar to each other or not. This is one of our super IATAs that covers the oral route of exposure. So it's an oral IATA, and it has a series of, as I've said, decision nodes with yes, no answers. These are some answers or some information for the user to guide you through the decision node. So this IATA focuses on dissolution as being a key physical and chemical characteristic that determines whether you're exposed to just the dissolved material or whether you're exposed to a mixture of the nanoform and dissolved material. So at this end here we have very quick dissolution rates as indicated by a half-life of very short duration, through to more biopersistent low solubility materials with a very high half-life. So first of all, we assess dissolution in the gastrointestinal fluids, and this allows us to decide whether our nanoform is instantaneously dissolving, quickly dissolving, gradual, or very slowly dissolving. For the instantaneous dissolving nanoforms, then we just assess their toxicity based on their composition and their constituent ions or molecules. For those that are dissolving quickly, gradually, or very slowly, we need to consider their dissolution inside the cell in a compartment known as the lysosome, where there is a pH of 4.5. And again, we've used half-lives to indicate their rate of dissolution so that we can decide whether they are not biopersistent, or highly biopersistent. Once we have that information, we then assess the toxicity of the nanoforms and the constituent ions, or just the nanoforms on their own, in order to decide whether they're sufficiently similar to each other to be grouped. So just to summarize, this IATA includes dissolution in the gastrointestinal tract fluid, dissolution in cells, and then an assessment of hazard. To consider hazard, we have a range of different endpoints which need to be considered, such as surface reactivity, cytotoxicity, ability to induce inflammation, and also genotoxicity. Behind each of these decision nodes is a tiered testing strategy with 3 different tiers. Tier 1 being simple methods such as in silico, in chemico, or in vitro methods. So in silico is computational modeling. In chemical is just chemical testing, and the simple in vitro models would just be a monoculture of one cell type. Tier 2 would be more complex models such as 3-dimensional multi-lineage pathophysiologically relevant cell cultures, and Tier 3 might be animal models. At each tier, we encourage the user to review the existing data available to them rather than going straight to testing, and only do testing to fill data gaps. As you move along the tiers, the level of certainty of the data that you generate probably should increase. And this is important when we think about the purposes of doing grouping. So tier 1 methods are often sufficient for safe by design, but if there's too much uncertainty, you can move to tier 2 methods. For regulatory purposes, tier 1 may be sufficient, but it's likely that in some situations you may need to move to tier 2 or even a tier 3 method. So as I've said, there are a range of SOPs or standard operating procedures available to us. At the tier 1 level, there are some regulatory accepted methods available provided by organizations such as the OECD and ISO. Unfortunately, at the tier 2 method, there are very few or no regulatory accepted methods available. For the skin, there are a few, but for other organs, there are none really. Projects such as Patrols have started to publish such models, which will be useful in future as evidence increases to understand more the certainty or uncertainty of the data generated by such models. And then tier 3, there are a large number of regulatory accepted methods available. So this is what a tiered testing strategy looks like. It's quite complicated, so don't panic. So along the top here, we have the different decision nodes, and then below we have the tier 1, tier 2, and tier 3 methods indicated, with reviewing the existing data indicated for each tier. And then within each box for each decision node, we've indicated the most relevant standard operating procedures that are currently available for people to use. So just to recap the GRACIOUS framework, so you can enter with a single nanoform or a provisional group. You collect your basic information in terms of phys-chem characteristics, release and exposure, and identify the purpose. You generate your grouping hypothesis. You test your hypothesis using the IATAs to populate a data matrix, and the level of certainty you need is dependent upon your purpose. You can then accept your grouping decision, refine your grouping hypothesis, or assess on a case-by-case basis. So once you've done your grouping, you can use this to fill data gaps for hazard. You can help to inform exposure information or risk information. It can feed into the design of risk management measures, and it can help to inform the safer design of new nanoforms in the future. So thank you for listening to this presentation, and we'll discuss some questions in the discussion session. Thank you.
Good afternoon. My name is Agnes Omen. I'm from the RIVM, the Dutch National Institute for Public Health and the Environment in the Netherlands, and we are partner in the GRACIOUS project. Today I will present to you some background on read-across in a regulatory setting. So first of all, what is read-across? Read-across is a commonly used alternative approach for data gap filling in registrations submitted, for example, under the REACH regulation. So this is important in view of the 3R principle, the reduction, the refinement and replacement of animal research. And of course, it can be important to save resources. In read-across, existing information of similar substances or materials is used to fill in or predict properties of a substance or material under consideration. So this really tries to make use of existing information. Read-across can be used in general, generally for multiple purposes. So for safe by design, for example, it can be relevant during the innovation process to learn about the toxicity of similar substances of materials, and this can help to target subsequent testing. But here I would like to focus on read across in a regulatory setting to fill data gaps in a regulatory dossier. And as the REACH regulation provides the most advanced guidance, I will focus on that and briefly mention other guidances in the end as well. So as I said, the focus of this presentation is on read across in a regulatory setting. Here it is indicated that read across requires structural similarity. And a read across hypothesis needs to be provided, and this hypothesis should give an explanation why read across is possible. It should be scientifically justified and documented. First of all, I will give you some background on read across of substances in general, and then focus a bit further on read across for nanoforms. I will not go into the definition of a nanoform and also not on the definition of a set of nanoform. First, some terminology. The terms source and target are used often. A source substance or a source material contains existing information. So it can be a single substance or multiple substances with existing information, and this information is used to fill in this data gap or to predict information for a data gap for a target substance or material for which the predictions are made. So these are important terms. And then here on the slide you can see the front page of the ECHA report on a read across assessment framework, the RAF. And I always wonder if this person here sitting with this extraordinary view is having deep thoughts on read across, or perhaps just wondering about something else. Anyway, a few other important terms are analog approach and category approach. An analog approach is used between a small number of structurally similar materials. So there's no trend or regular pattern on the properties of those materials. And the differences between the different substances should not influence their toxicity and fate properties. In a category approach, this is employed when several substances follow a similar pattern. So they have a structural similarity, and for example, there is a similar pattern looking at the chemistry where the carbon backbone is increasing in length, or there is a functional group attached to this carbon backbone, and this also have changes in a regular pattern. So this may be used in a category approach, and then a prediction can be made for one of the substances within this pattern. Also, a worst case approach is possible. So here the strength of the effects of the target substance is expected to be lower than the strength of the effects observed in the source substance. So the source, where you have the existing information, is having a higher effect than the target, and you can indicate this based on both kinetic considerations, for example, information on the bioavailability, and on potency considerations, and these should be combined. So with that, in this RAF framework by ECHA, there is this overview of different scenarios related to the analog and the category approach. So you can have the analog approach here on the left with an hypothesis, and for example, there's the hypothesis that due to biotransformation, you end up with the same compounds. Then this is one scenario. And another is that the different compounds or substances have the same effects, another scenario. You can have a similar approach for the category where there is variation among the category members following this regular pattern, or there's no variation, and then you both can have this scenario with biotransformation leading to the same substances, or that the different compounds have the same type of effects where you can have this other scenario. This is most of the information on substances in general. As indicated, read across for substances requires this structural similarity, either this common related to, for example, this common functional group or a constant pattern, but this is all chemistry. And now we come to nanoforms. And as we all know, there's also the physical aspect related to nanoforms. So let's say a titanium dioxide particle of 10 nanometer can have, of course, has the same chemical structure or the molecular structure as a titanium dioxide particle of 120 nanometers. But there are still differences. So for nanoforms, this is used in general only for within the same substance, so only within the titanium dioxide. But then the molecular similarities, the molecular structure, the TiO2, is not sufficient for read across. There needs to be more than just it is also TiO2. And this is elaborated further in this ECHA guidance specifically for nanoforms. So this guidance indicates by seeking similarities in physical chemical properties, so not only the chemical but also the physical, toxicological behavior and fate, and ecotoxicological behavior between the different nanoforms, it is possible with those physical chemical parameters and also in vitro screening methods to develop a robust scientific explanation for read across, for grouping and read across. And a stepwise strategy for grouping of nanoforms is indicated in this guidance. It is pretty small, but I will try to give you the headlines here. So the first step in this strategy is to identify and characterize the nanoforms and sets of nanoforms of the substances. So first we have to know what are the nanoforms we are talking about. And then there is this overview of physical chemical properties that needs to be available. And then we focus for the characterization on this part: composition, impurities, surface treatment, functionalization, size, shape, and surface area. So this is the first part: identification of and characterization of the nanoforms and set of nanoforms. And then initial grouping is proposed. So you have to develop a hypothesis for a specific endpoint or for several endpoints so this hypothesis needs to be there. And then you have to gather the existing information for each of the members of the groups that are in this initial grouping hypothesis for the physical chemical properties, but also for toxicity, fate, toxicokinetics, etc. And then it is indicated again in this figure that properties indicated here in yellow are the solubility, hydrophobicity, zeta potential, dispersibility, dustiness. They relate often to the behavior, to the fate and toxicokinetics. And then the properties in green, biological reactivity or photoreactivity, they relate often to the reactivity and hazard of the materials. So these often, the properties in yellow and green, needs to be indicated and substantiated in the hypothesis where relevant. With all the existing information, a data matrix should be constructed with information on these properties for each of the members of the potential group, and then assess the applicability of the approach and fill in data gaps within the group. So is the data matrix well, sufficiently filled? And also, does this help to justify the hypothesis? And if this is the case, you can document the approach and justify the results. And it may also be needed to further fill in the data gaps to get an overview of the whole group. So you can have to do some testing if needed and evaluate there also if the grouping is justified or not. If not, you can try to fill in or go to another hypothesis, which is of course also possible. So looking at this, this is in general a very useful approach, but still a general one. And Gracious aims to develop practical approaches to facilitate the grouping and read across of nanoforms. So really using also this regulatory setting as a background, how grouping and read across can be used and made practical for nanoforms. And further information on this will be provided by Nina and Richard in the subsequent talks. And with that, I would like to draw your information to further information. I already showed you the Read Across Assessment Framework RAF by ECHA and the guidance on specifically for nanoforms, the R61 appendix. And then there are two other guidances where Read Across is mentioned by EFSA and by SSES, so on food and feed and on cosmetics respectively. And in both cases, it is indicated that read across of nanoforms is possible on a case-by-case basis. And in both guidances, reference is made to the ECHA guidance, so it is very much in line with that. And with that, I would like to thank you for your attention, and I welcome any questions later on. Thank you.
Okay. Effectively, and hopefully you should be able to see myself and Agnes Uman on the stage now. So I'm Vicky Stone. We also have Richard Cross and Nina in the green room, so they may contribute to the discussion by the discussion forum at the bottom of your screen as well. So we have a couple of questions in the live Q&A, so thank you for posting those. The first is from Magali Forret, which is, some structural toxicity behaviours may be limited to a specific endpoint only. How can we make use of this in regulatory programmes like REACH, where groups of nanoforms should consider all endpoints, human health and ecotox? This is a really good question. And what the Gracious framework helps you to do is actually prioritize exactly what you're saying there is the most relevant endpoints that you want to assess in order so that you don't have to test everything. But what they're asking you to do is to make sure you don't just focus on one route of exposure for humans or just humans and ignore the environment. So I think where you've not got any particular hazards or risks associated with a particular exposure route or endpoint, you just need to justify that potentially in your document. Agnes, what do you think? Would that be correct?
Yeah, I think so. But perhaps this question also relates to the sets of nanoforms. And for a set of nanoform, you should be able to do, well, read across, or the toxicity should be similar for all endpoints. Different from when you look at a specific endpoint and just nanoform by nanoform and not go into the sets of nanoforms.
Yes, so grouping and sets of nanoforms are not exactly the same. So a set of nanoforms is when you've got a really, really similar group of nanoforms, and you can just consider all of their toxicity in every scenario to be the same. Whereas a group of nanoforms would be similar, but not so similar that they would have exactly the same toxicity profile in every scenario. I hope that makes sense. So that might be the issue behind that question. Okay, thanks, Agnes, for spotting that. And then we have a question from Van Rito about whether what the role of NanoInformaTIX is in the Gracious project, and are we using artificial intelligence? So Nina is going to talk after this discussion session on methods for assessing similarity. So we are using things like multi-component analyses to look at similarity across a wide range of data information and across different properties within a single IATA or within a single hypothesis. And so Nina will discuss that more later on, and she is responsible for the database eNanoMapper, which the Gracious framework links into so that we can link to existing data that has been generated from current and previous projects. So Nina may be able to answer that in more detail later on. Okay, we don't have any other questions in the current question Q&A session that I can see. So what we're going to do now is a little activity. Oh, we have one from Louis Mauricio. In your opinion, what are the future perspectives for the improvement of risk assessment for nanomaterials and nanoforms? What should be included? Are there any gaps? The biggest gap is understanding the long-term effects of nanomaterials in humans and in the environment. That is by far our biggest gap. There are very few long-term animal studies. There are very few long-term environmental studies, and where they do exist, they're with a limited number of materials and they're with a limited number of endpoints. And of course, we don't yet have epidemiological data. There have been pushes to get funding to fund people in workplaces exposed to nanomaterials in order to set up these monitoring programs so that people can be monitored and historical data can be collected, but that yet hasn't come to fruition as far as I'm aware, and it's certainly not published. Agnes, do you think there are any further gaps?
Yeah, well, I think exactly this long-term, the existing data for long-term toxicity is still limited. And if you want to use grouping and read across, you want to make use of existing information. And if there's little existing information, also doing grouping and read across is limited somehow. But I think this will improve, of course, in the future. So that will help anyway. And
yeah.
Now we also
go on, sorry.
Yeah. Now we also go into a phase where the regulatory application of grouping and read across of nanoforms will find its way. So I see what applications are accepted and what not, and we can learn from that. So I think the coming years will be very interesting from that point of view.
Well, there have been some really interesting developments in terms of defining adverse outcome pathways. So adverse outcome pathways, or AOPs, are sort of mechanistic pathways. So they identify the initial initiating event, the molecular initiating event, so the thing that causes the particle to generate a cellular or tissue response, and then all of the steps, the molecular steps or key events they're called, that then lead to an adverse outcome. And these adverse outcome pathways allow you to identify biomarkers that should lead to the adverse outcome, whether that's a long-term or a short-term adverse outcome in the future. So what projects like Gracious have done is exploit these adverse outcome pathways to generate these IATAs so that you're asking the questions that relate to these key events that are associated with disease. And that means you don't necessarily need to wait 3 years or 5 years to see a disease outcome, because you can look at these earlier biomarkers to help with that. But they do need some long-term validation with these long-term endpoints as well. Okay, we're going to do a quick activity. So you all need to go to the discussion forum. So if you can just click on the discussion forum at the bottom, and I just want you to give me an example of a nanomaterial that you are working with, you have worked with, or you're interested in. I want you to tell me a little bit about its phys-chem characteristics, maybe its shape and its size and its composition, and maybe what it's being used for. So if you can just give me an example, I'm going to type one into the chat now, so I'll give you a few minutes to do that. Okay, so I've posted mine in the discussion forum. So if you can post an example of a nanomaterial, something about its phys-chem characteristics, and what it's going to be used for. And hopefully Richard and Nina can also contribute to this from the green room if you're listening. So Luis has put a titanium dioxide and silver nanoparticles with different sizes, with coating and uncoated with PVA. That's brilliant. Richard's put a zinc oxide particle, 80 nanometers, no coating, used in a paint. We've got a silica 15 nanometers food additive from Burkhard. And we've got a titanium dioxide food additive, uncoated, from Agnes. And then Fatima's got a nanocellulose fibril, 20 to 40 nanometers diameter, several micrometers in length, in paper and card. And then Jose's got titanium dioxide, uncoated, and a zinc oxide uncoated. And then Andrea has got titanium dioxide. So just wait a couple more seconds for people to put these in. So we've got some carbon nanotubes to be used for treating Alzheimer's disease. I'm not sure about that one. And then titanium dioxide uncoated, pure anatase. Okay, so what I want you to do is I want you to go through the list and try and pair some nanomaterials that you think might have similarity, either similarity in potential exposure routes and or similarity in their phys-chem characteristics. So can you try to start thinking about how and why you might group some of those nanomaterials together? So I can see an obvious one for me. I would look at whether I can assess the similarity of my multi-walled carbon nanotubes with Yvonne's carbon nanotubes for the Alzheimer's disease. And there was a fiber, a nanocellulose fibril as well, because it has a high aspect ratio, or it's a fiber-like material. It's probably quite different, but it'd be interesting to see how similar it is. So there's my example. So go through the list and see if you can find something that you compare or group your nanomaterial with, and then post it in the chat, and we'll have a look to see what ideas people come up with. Okay, so Richard, you said zinc oxide with a coating. So is this the one that you would, could you say what you would compare the zinc oxide with? Agnes, could you give an example of what you might pair your material with as well for people to see, please? Thank you.
Yeah, well, for titanium dioxide, there are many different nanoforms which are all E171. So you have, yeah, so it's a group in itself. So you have anatase, you have rutile, you have different size distribution. So yeah, that would be a grouping within, well, all the different E171 forms.
Okay. Okay,
Looking
that's
for the
great.
oral route. Yeah.
I'm conscious of time, so I think we should switch to Nina's presentation now. The time went quicker than I realized. So I will have a look in the chat while Nina's presentation is going on and make some comments. So thank you. We'll hand over to Nina's presentation now.
Good afternoon. My name is Nina Zhelyaskova. I'm co-owner of SME Idea Consult Ltd based in Sofia, in Bulgaria. The focus of this talk is Introduction to Similarity Assessment and Approach pursued by Gracious Project for Estimating Nanoform Similarity. Why similarity assessment of nanoforms? Like a guidance on QSR and grouping of chemicals, and specifically the 2019 appendix for nanoforms, indicates that looking for similarities in physical properties, toxicokinetic behavior and fate, and ecotoxicological behavior between different nanoforms may be possible to substantiate the assumption of similar hazard properties between different forms of a substance. The guidance suggests using physical properties and or in vitro screening methods, so it doesn't provide details on methods to estimate similarities. This is not really an exception compared to the guidance on similarity for both substances. However, to facilitate read across for nanoforms, the partners in Gracious project are exploring different methods and compiling recommendations. The findings will be published in a white paper and a series of use case publications. First, let's have some definitions adopted by the Gracious Similarity Task Force. A property can be a basic physical parameter, for example, size, surface area, shape, surface treatment, required to identify a nanoform. Or it could be a property to describe an aspect of nanoform interaction with the immediate surroundings, for example, reactivity or attachment efficiency. A scalar descriptors is a single number accompanied by units of measurements, for example, nanometers. Examples are median of particle size distribution or lowest observed adverse effect level for the dose response curve in inhalation toxicity. A data matrix is a matrix containing all and only the descriptors required by the IATA to a specific hazard. The role of the similarity assessment is to help taking a grouping or read across decision about the candidate group members. The main message here is to convey is that we assume we have compiled a data matrix and we perform a similarity assessment based on this data matrix. This slide shows the structure of the data matrix for particular hypothesis. It includes properties, size, specific surface, long deposition, dissolution, reactivity, and inflammation, each with one or more scalar descriptors. For example, for dissolution, we have dissolution rate and half time. We can then use the entire data matrix on only the four properties marked with crosses, which the four properties which expert identified as best one for this particular hypothesis. Once we have identified the properties, we can apply different similarity methods. This slide illustrates perhaps the simplest way to calculate similarity by X-fold, basically the ratio between two values, the largest value divided by the smaller value of two scalar descriptors. We can look at quickly soluble zinc oxide NM110, which is a benchmark material in this case, which has a dissolution half time very low, which is indicated on the left side. And on the right side, the zinc oxide is on the second row on the right side. We have the pairwise similarity matrix, where each cell represents similarity value between pair of materials, for example, zinc oxide Nm110 and titanium dioxide Nm105. Two types of cereals, and then barium sulfate and two iron oxides. The second iron oxide, nanoform B, has a very high dissolution half-time and hence is very different. Then this is indicated in the similarity matrix with red color and the X-fold value on the maximum X-fold value of 15,000. Apart from X-folds, there are many ways to calculate similarity, and these are defined by distances or similarity index. Let's have a look at a familiar definition for distance on a map. The distance between Sofia and Madrid on a straight line, the yellow line on the picture, is 250 kilometers. This could be considered a two-dimensional distance. Its length can be calculated using the length of the blue and the green line by the Pythagorean theorem. Of course, if you assume the Earth is flat between these 2 points. And the length of the green and the blue lines are one-dimensional distances. You could imagine these are not the only possible way to calculate distance between Sofia and Madrid. For example, the driving distance will be much longer, about 3,000 kilometers. In general, a distance between 2 points is the length of the path between the 2 points, and the path doesn't need to be a straight one. Now go back to the distances between numerical properties. Here is an illustration of different distances between point A and B, defined on the plane with descriptors x and y. The length of the blue straight line is the Euclidean distance. The red line defines another distance, which is known as Manhattan distance. On the right, the length of the blue line defines the two-dimensional Euclidean distance between the zinc oxide and barium sulfates using the reactivity descriptor on y-axis and inflammation descriptor on x-axis. Once we have the multidimensional distance calculated between each pair of nanoforms, we can populate the pairwise similarity matrix, where each cell corresponds to the integrated similarity across all relevant properties between pair of nanoforms. As already mentioned, there are many ways to calculate similarity between scalar descriptors, and here we show Euclidean distance on the first column, again Euclidean distance on the second column, but on using transform data, and finally X-fold on the third column. The first row of matrices shows the pairwise similarity matrix for dissolution rate. The second row shows the pairwise matrix for half-time dissolution, half-time. And half-time X-fold matrix is the same as shown previously. And it can be noted again that Nm110 zinc oxide benchmark materials is also prominently different than other materials, but the values, the color shade, are not exactly the same. And please note there is a difference between the first and the second column of matrices, even if they both use Euclidean distance. The matrices in the first column use the original data, while for the second column the descriptors were first normalized and log transformed. Why it's important to normalize and transform the descriptors? First, normalization means all the descriptors are scaled into the same range, usually between 0 and 1. This is important, especially when using multidimensional distances. Otherwise, descriptors spanning large range will dominate other descriptors used in the multidimensional distances. The need of a log transformation or a similar transformation might be less intuitive, but its goal is to transform skewed distributions like the one we have on the left, the blue one on reactivity descriptor, to a normal distribution, more or less normal one. The log transformation is not the only one to be used. The transforms as Box-Cox or Yeo-Johnson transform can be used instead of logarithmic with the same goal. It's also important to include the representative test materials for each property. Otherwise, we'll not be covering the entire possible range, entire relevant range for the property, and our results will be skewed. Here, an example of similarity of in vitro toxicity is demonstrated using 5 different methods. Euclidean distance with log transform data, X-fold, rsync, OWA-based similarity, and Bayesian factor similarity. The latter two are new methods developed by Gracious partners. They'll be described in methodology manuscripts which are currently under preparation. All algorithms now confirm the choice of benchmark materials which are not similar to the case studies. For example, look again at the second row where zinc oxide NM110 is almost everywhere shown in red. Ranking in most algorithms are consistent, while numerical threshold of acceptable similarity need to be different per algorithm, but can be made to result in the same groupings. And this figure also illustrates the importance of data transformation toward normal distribution when using Euclidean distance, using either log transform, Box-Cox, or Yao-Johnson one. Finally, preliminary results on limits of acceptable similarity are presented here. This is a result of Gracious Similarity Task Force. As indicated in the previous slides, these thresholds are different per algorithm, but can be set up to result in the same ranking. With this, I'd like to thank for your attention and will be happy to questions. Thank you.
Hello and welcome. My name is Richard Cross. I'm a researcher here at the United Kingdom Centre for Ecology and Hydrology, and today I'm going to be talking about the environmental case studies for similarity, grouping and read across that we developed within the Gracious project. Now you will have seen Vicky, Agnes and Nina's presentations before this, so I don't want to go into too much detail about the specifics of what grouping means. Suffice to say that as a recap, grouping is a general approach that allows us to assess more than one chemical at once. And importantly, when we consider nanoforms, more than just the chemical identity should be considered. Other properties need to be discussed. And that's because a nanoform may also have a specific size, shape, or surface chemistry, as well as the chemical identity of the material itself. Now I'm going to give you a brief overview of the environmental hypotheses that have been developed within the Gracious project. We have a range of general hypotheses that have been developed. Those in orange are highlighted, which are hypotheses for where they go, for the environmental fate of the particles. And they're based around the dissolution rate and dispersion stability of those nanomaterials and the various outcomes for grouping which arise from the combination of those two properties. In blue, these are hypotheses which are related to biopersistence and chemical transformations, whilst in green, these are actually the hypotheses which we've been dealing with specifically at UKCEH, which is looking at coating durability against biodegradation as a way of grouping nanoforms with different surface treatments. As well as the general hypotheses, we also have some compartment-specific hypotheses for those in sediments and in soils. Now, as you will have seen from the introduction to the IATAs in an earlier presentation, what I'm going to do for the environment is go through a few examples about how we've used existing information to inform the thresholds in decision nodes in these IATAs. I'm going to use EG1 as an example of this. Now, this was the hypothesis which delivers various grouping outcomes based on the balance between the dissolution rate and the dispersion stability of your nanoforms in the aquatic environment. Now, the Gracious IATAs guide collection of the evidence that you need to accept or reject this grouping hypothesis. And importantly, that IATA specifies the most relevant tests to make that decision. Now, if we zoom in on the blue box down at the bottom here, what we can see is how our grouping by where they go, so this is the environmental fate of your nanoform, identifies both the relevant compartment for assessment, the form of the exposure, and the apical hazard endpoints of concern. So Gracious has identified a number of key decision nodes that identify what the hazard endpoints are that are relevant based on the fate of the nanoform in that environment. So, for example, it might identify whether a particle remains as a particle or dissolves into its solutes, and which of these is responsible for toxicity. Another example can be whether it identifies aquatic or sediment toxicity as being of concern. Now, to quantify the cutoffs and thresholds that are required for dissolution rate and attachment efficiency in this hypothesis, work by Mesters, published in 2019, did a sensitivity analysis for the simple box for nano modeling, modeling nanoparticle stability in this generic aquatic environment. And it identified a threshold of around 10 to the minus 4 for attachment efficiency. And when you're below this threshold, most of the particles remain free in dispersion, so you have a stable dispersion of your nanoform. However, once you go beyond this threshold, heteroaggregation and attachment dominate the particle fate, so your nanoform becomes less stable as the attachment efficiency increases, and you might lead to sedimentation and identification of sediment toxicity as being relevant for these particles, for example. So this sensitivity analysis has been performed across a range of environments, allowing us to identify thresholds in red, above which your PEC, your predicted environmental concentration, may increase or decrease with that change in transformation rate or change in attachment efficiency. Now, when nanoforms are actually beyond this threshold, they enter a range where the PEC is sensitive to changes in these properties. When you're in these range, for example, those highlighted in blue here, a category approach to read across could be used to predict PEC on the basis of a regular trend. Alternatively, as we saw in Nina's presentation earlier, similarity assessment on individual properties of the nanoforms grouped in this applicability range could be used as part of a read across justification. So I'm now going to give you a detailed example using the case study that we were testing at UKCEH, which is grouping nanoforms based on the resistance of surface modifications to biodegradation. And here's just a list of some of the people who were involved in this work, partners with us at UKCEH, but also at LATAT in Spain. Now, the rationale for this grouping hypothesis is that there are a likely near infinite number of coating nanoform combinations, especially if you take into account that you can have the same coating material if it's a polymer, but it might have different chain lengths or different surface coverage as well. Now, this means that it's simply too diverse to test every possible combination. However, we should not assume that if a coating differs between nanoforms that you cannot group, because this would be too restrictive. This is exactly the kind of case that grouping might be useful in allowing us to reduce the testing burden across different nanoforms. So first of all, we have to define our hypothesis. Well, we know that surface treatments may modulate the nanoparticle behavior and toxicity in the environment. However, we also know that these surface treatments may be lost. And in this case, if we have a surface treatment which is degraded in the environment, and it is no longer present at the surface of the material, that would allow nanoforms with ostensibly different surface treatments to therefore be considered similar on the basis of a similar low durability of these surface treatments. So they no longer are involved in driving the fate and hazard of these particles. Alternatively, you could have nanoforms where the surface treatment persists but is not toxic and does not change the toxic profile of these particles. In this case, nanoforms with different durable surface treatments may still be grouped according to other IATAs if it is found that they are similar according to both where they go and what they do. I.e., this means that if you have two particles with different surface treatments, if, for example, the attachment efficiency and the dissolution rate doesn't differ between those two particles, they may still be grouped by that generic hypotheses that I described earlier. There is a third case where the surface treatment persists but is also toxic. And in this case, nanoforms might be grouped for where they go. So you might be able to read across for predicting the environmental concentrations of these nanoforms in various environmental compartments. However, you cannot group for where they do, as specific toxicity of the surface coating must be considered in their risk assessment. So for this hypothesis at UKCH, we have developed a tiered testing strategy to answer this question over whether the surface treatment is biodegradable. Now, to do this, we've optimized and adapted a well plate-based MT2 screening assay that can screen for whether the surface treatment chemicals are biodegradable. Now, what's important when you have these tiered testing strategies is that the lower tiers should be predictive of your higher tier test answers. And in some cases, you can get a result which is sufficient to answer the decision node. However, in other cases, your lower tier test outcome may trigger higher tier testing if a decision cannot be reached on the basis of that lower tier outcome. So the principle behind the tests that we've developed and optimized at UKCH is that we take the MT2 biolog microplates, and this is a colorimetric carbon utilization assay in which we inoculate our plates with microbes isolated from sewage sludge, and then we introduce our test substances as well. And by monitoring the colour development, this acts as an indicator of microbial respiration and organic molecule biodegradation. And from this, we can calibrate against a reference carbon source and calculate the percentage of your chemical that was biodegraded within that well. The aim of this is to use this assay as a screening approach to identify organic surface treatments that may be biodegradable, and those from which assessment may benefit from escalation to a higher tier test. So we needed to validate our screening assay by comparing the outcomes that we got from the MT2 assay we developed at UKCH against the outcomes and results you would get from the standard OECD 301 method, which was performed by our partners at LATAT. Now, we've tested 20 common chemicals and used the OECD 301 test to calibrate thresholds for our MT2 assay. So one example of this is that we found that citric acid is correctly identified by both the MT2 assay and the OECD test as readily biodegradable. So one question that we have is, can a threshold for percentage biodegradation in our screening MT2 assay be defined for readily biodegradable substances? Now, citric acid was a benchmark for our readily biodegradable coating, but for our non-biodegrading substances, something like PVP, we've identified as, again, successfully being identified both by the MT2 screening assay and the OECD as a non-biodegrading substance. Now, the aim of our MT2 assay is to be a precautionary screening step. So where we see positive biodegradation, we need to have good certainty that biodegradability is possible. Whereas whilst we see no biodegradation, that may actually be a cause for escalating to a higher tier test. So here is a summary of the results that we have so far, comparing between our tier 1 test in the left-hand column and our tier 2 test, which is the OECD test, in the right-hand column. And to summarise, we have 15 complete comparisons to date, and 12 of these results are in good agreement. For 4 substances, we have outstanding data. 2 of these were insoluble, and so weren't suitable for the MT2 assay, and 2 interfered with the test, thus requiring further method development. However, of the data that we have so far, it does indicate that the MT2 assay does deliver a precautionary grouping decision successfully. And this is because within our comparison and our calibration against the OECD results, we found 3 false negatives. So this was where your tier 1 did not identify biodegradation, which was then observed in your tier 2. However, we saw no false positives. So we never got a result where we saw biodegradation in the MT2 assay, but observed no biodegradation in our OECD assay. So that's nice, because that does mean that this MT2 assay is precautionary, where if we see a result, a positive response in the MT2 assay, we know that a positive response would also be observed in the OECD test. However, we know that if we don't see biodegradation in our MT2 assay, this could be a trigger for escalating to a higher tier test to see whether this is a false negative or whether there actually is no biodegradation of that chemical. So to recap and summarize, general environmental and compartment-specific grouping hypotheses have been developed, and the thresholds for these IATAs have been informed by existing modeling efforts where possible to allow us to answer decision nodes in these IATAs. Specifically for our example of coating degradation, an IATA for this grouping hypothesis based on the durability of your organic surface treatments has been developed. And we've also introduced a screening tier 1 assay adapting the MT2 plate colorimetric test, and we successfully employed this to screen for biodegradation of organic surface treatments, acting as a tier 1 assessment for this decision node in our IATA. So thank you very much, and I look forward to the discussion session at the end of today. Thank you.
That's great. Thank you very much. So thanks to Nina and Richard for their presentations today. And we have one question in the live Q&A session for Richard. So what if the surface treatment affects the fate of the substance in the environment or its mobility? Can we still read across to a different coating or no coating? So Richard?
Yeah, that's a really good question. I think it depends on the fate routing that you're expecting that material to take. And what Gracious allows you to do with this IATA is if you expect, for example, the fate routing of going through wastewater treatment plants that we described in that previous presentation, if you know that's the pathway of your material and you can observe degradation of that coating within that compartment, then for the subsequent exposure in water, you've demonstrated that that coating will no longer be driving the fate of the particle because it will be lost. And so in that case, you've lost the coating and it no longer is playing a significant role in the behavior and thus toxicity of that particle subsequently in the environment. However, we can also have the inverse where even if we demonstrate that the coating is not lost in the environment, it could be then that you can still you can still group those particles, even if they had different coatings, but you would have to demonstrate that both the fate and the toxicity of those particles was similar.
So in summary, if their fate's not the same, then it's difficult to justify them being similar. Is that right?
Yeah, and unless you can demonstrate that this coating is lost and no longer driving the fate.
Okay, that's great. So we don't have any questions posted for Nina, either in the live Q&A or in the discussion forum. So if you look in the discussion forum from the previous session, you'll see that I've posted some comments in relation to the discussion that was going on there from the previous session. But now we're going to move on to a different question. So on a couple of occasions, especially myself and Agnes referred to a data matrix, and that you need to generate a data matrix that has all the information in it that you need in order to do the similarity assessment that Nina described. And then Richard described to you an IATA, which is the questions or the decision nodes that you need to go through and some of the methods that you would use to answer those questions. So it's the data that goes from those assessments, from those methods, from the IATA into the data matrix. So if you were designing a data matrix, what would you need to include? Okay, so have a think about what things you would include in a data matrix. Post your answers in the chat. So if you've got any ideas of things that you would include. I'll give people a minute to type because it'll take you a minute to think and a minute to type your answer. Data, thanks, Daniel. Yeah, data for what, though? Nanoparticle features from different nanoparticles. One feature creates a different matrix. So you need to name your nanoparticles. So you need to give your nanoparticles a name. So many of the particles that we've used in the Gracious project and other European projects come from the JRC repository, and they have a code. That code used to be NM and then the number. Now there's a longer code and that number at the end. So you need to name your particle. You need to put something in about the physical and chemical characteristics. So you want to know the size, you want to know the shape, the composition. So all of those things would go into your data matrix. What else would you put in there? Yep, so size, shape, dissolution rate. So dissolution rate is actually a really key parameter. It's key both on the human health side and in the environmental side. It's one of the most important parameters that we measure at the tops of our IATAs, because it really distinguishes the fate of the nanomaterial and also its biopersistence. So it's a really key one. Attachment efficiency. So Richard talked about attachment efficiency. That's very relevant in the environment. And then hazard data. Yeah. So essentially what you have is a grid. A matrix is a grid. And along the top, we put the nanomaterials or the nanoforms. And then the rows are the properties that we're measuring. So the size, the shape, the composition. But those properties are also their hazards. So they're hazards in an in vitro model, or their surface reactivity, or their ability to induce a tumor in an animal. Okay, so your data matrix is all of that information combined. And then if you've got it side by side for each nanoform, that allows Nina or somebody else then to do that similarity assessment. So data that's harder to gather in vivo is less practical for screening. Absolutely, completely agree with that. And that's why we have tiered testing strategies behind each of the decision nodes. So we prioritize the use of non-animal testing throughout the IATAs so that you will reduce that reliance on the animal testing. You will need some animal data, some tier 3 data, in order to calibrate or to understand the relevant biological range of your data for some of the nanoforms in your group, and that will support the read across then for those nanoforms that don't have that animal or tier 3 data. So constant properties that are relevant to the specified AOPs, exactly. So all of these decision nodes are aligned with the key events in an AOP. So yeah, that's perfect. Magla, broadly available data that would support grouping is so any, I mean, the trouble is to understand exactly what data you need to support grouping. And that's why the IATAs are useful, because they help you to focus. You need to have a hypothesis, and that hypothesis is really useful because then that helps you to focus on the data that you need to prove or disprove your hypothesis. So that allows you to identify that data that can support grouping. So that's some really, really excellent comments. Agnes, do you want to add anything to any comment people have made? Have I missed anything?
No, thank you. Clear overview.
Nina, did you want to add anything?
No, I think this is well said. And
Okay.
yeah.
Okay, thanks. Richard, anything else you want to add?
I'd add that the Gracious framework does give pointers for the basic information, which can start and guide you to what hypothesis might be most useful. So that is the place to start with your data matrix. And like you say, that describes what your nanoform is and starts to pull apart differences between them.
Yeah, it's a really, really good point. And Magla also makes a really good point in the chat there about looking at your best and worst case in your class. So yes, I think that's a really good point. We've never thought about positioning the nanoforms in a ranked order in our matrix, because it maybe they might rank differently for different properties, but especially for some of the hazard endpoints where you want to do that read across, yes, it would be good to know which is your worst case material in your group, and because that actually might become your source material. Because when you do read across, as Agnes said earlier on, the substance that you read across to your target should usually have a lower hazard than your source material, just for safety's sake, for being cautious. Okay. We just have a couple of minutes left. I think unless there are any other questions, we probably should stop there, because we don't have time to start a new activity. Okay, so thank you very much, everyone, for participating. Thank you to Agnes, Nina, and Richard for presenting today and contributing. And thank you to Stella and Danal and others for organising the Nanosafety School. And we hope it's been useful. Thank you.